before I get started, I have to apologize. My demonstration that I plan on giving today is going to be a very poor demonstration. My Facebook announcement just got out there, right? Yeah, they're using our room for something else, and if everyone shows up, this is a small room, so So I'm going to go through a couple sets of slides relatively. I said last week that it was going to be probably a long class. It's probably going to be relatively short. But before I get started, let me just kind of talk a little bit about the report that you're supposed to submit. And this report really doesn't have a fixed format but what I'm looking for on this report, and someone sent me a Facebook message that for whatever reason I have not been able to apply to reply. We're sorry, but someone kicked us out of our classroom. I don't know who does room scheduling, but they just totally ignore classes. I think the assumption is that all the classrooms are empty from 5 o'clock on, so they just grab whatever classroom they want. Okay. When did I set the due date for this report? I think it was after the break, right? Or was it this Friday I said? Anybody remember when I set the due date for the report? Did I set a due? I think I set a due date on e-learning actually. When I go to e-learning, I think there is a due time that there. I'll take it all the way through the break because I won't grade it until after I get back. And next week during the semester break, I am taking vacation that week, and I'm going to go sit at a hotel on a beach someplace and smoke cigars and jumping in and out of the pool at the hotel and relax. Eat good food at there. So, and listen to my wife complain about how we're spending too much money on vacation, but I don't care. I need to get away from KL for a week or so. Okay, this report. The first thing you should have is an introduction, right there. And what is the goal? And I'm sorry about my handwriting, but that's what it there. What is the goal of this report? In this report, or this project, and welcome, Yeah, hopefully everybody finds us if not, they'll end up watching the recording. They may go there and see the room's busy. And did my Facebook message get out? Yeah, it did get out. So most people have Facebook on their computer, on their phones anymore. So, but what is the goal of this project? And the goal of this project really, I'm going to just say, is to be. I have somebody's comment that there. The goal of this project is to simply become familiar with the robot. That's there, and there. Again, I had you pick something up, move the arm around. Some of you picked it up and twisted it. Some of you picked it up, moved it, put it back. That's there. But the whole idea is that you could basically control the arm. That's there. So then, of course, the next part is going to be your procedure. And your procedure is basically how did you do the project? How? And there was two parts of the project. One was to figure out 180 degrees for each one of those motions, and then try to figure out how to pick something up. And I suspect most of you probably just set it to some angle, and then that's where you put your spot, because I didn't give you an exact spot to pick it up from and move it to. Now, in real life, you would have an exact spot. You can't move the. If your goal is to pick up an object from one conveyor belt and move it to another conveyor belt, or move it into a box or something, a shipping container, you can't move the conveyor belt, so you have to figure out how to get to that particular spot on the conveyor belt. But here, the whole idea is just to get used to the robot there. How did you do it? Do the project. Now, of course, part of this right here is you're going to include the code right there that you wrote right there. So that there are any drawings you did there, because again there was two parts. One was 180, showing the 180 degrees in each motor, and that would be basically a drawing that you would include that there. And then the last part is just simply a summary or conclusion, right there, and did it work? What did you learn? Right there. What problems? And my pen is definitely giving me issues here. Maybe it's my brain's not connected. Did you have? So again, you basically have a list of that there. And again, you should look at this report as not being more than a page or two. I mean, that there. Now again, this is put into the e-learning Dropbox. That there's anybody found the e-learning Dropbox that there? But if you go into again, here's mine. If I bring up, actually I can close that right there. Work, EKL. If you go to that there, e-learning, e-learning down here, students, that there, and their e-learnings, I should point out there that, and somewhere in here, there's my courses, here's my courses here, automation, is that there's stuff from last year there too. But I put the report here. Again, you just submit your report right here. Now mine's different because I see that two people have already. What? Am I in your room? Oh, okay. Yes. Our accreditation's been approved for 3 years, which is one of the higher levels. So the electrical engineering department program ICO has now been officially accredited by PEM. Which means that this kind of side note is that accreditation is important in Malaysia, particularly. To be registered as a graduate engineer, the program you graduate from has to be accredited by what is the Bureau of Electrical Engineers Malaysia. That there, and that's a process that we've all been working on very diligently for 2 years, and especially Dr. Kyrell. I mean, Professor Kyrell probably did 90% of the work, and the rest of us probably did about 1%, 2% each that there. And I've been through accreditation processes in the U.S. about 6 or 7 times I've gone through, and I've done it as head of section. And I can guarantee the head of section does about 90% of the work. Because I was in his position about a year and a half before I came here that there, and I had 6 different degree programs I had to go through the process. He had 1, so I know how much work he went through. And congratulations, especially to Dr. Kyrell. And MFI, by the way, only got 2 years, so we actually did better than the mechanical group. So we got 3 years of accreditation, so which means that we can take a break and not work for so hard for the next one for a year. So just kind of that's just a very important announcement that it's important to you more than it is to me. Because when you graduate, that means your degree is a fully accredited degree in electrical engineering with honors. So you go on to be registered as a graduate engineer, go on to be registered as a I call it professional engineer. I don't know what the term they use, IR here is, that they're registered engineer, I guess, is what IR, because blaze different. They put the adjective after the noun, right? So say, I ought to correct Beirut means I got a blue car, right? In the U.S., they say I have a blue car. They put blue before that there. So IR is engineer with a spelling starts with an I. You have no choice when it's in the front now. If you're just coming there. The only 4 seats left are up in front. That's it. So, and the job market, the way things work in Malaysia, he's not going to sit in the front row. He's going to take the chair and move it back. You know, I did brush my teeth this morning, so my breath is not that bad. So, I don't know. Yep, I took a shower too. Regardless, that's just kind of a side announcement. I actually, the paperwork came in, and I was looking at it on my phone just as we were getting settled in, right there. And I don't know, it's somewhere in this list. Right there. And yeah, I don't see where it's at on this paperwork, but evidently that there is that we did get 3 years, so we're in good shape. Okay. I don't know. It's somewhere in this paper, this form that they sent out that they sent pictures of the report, but that's what Dr. Abraham had to come in and tell me that the word is out that we got the 3 year. Okay, back to our lab report. Basically, I have no set format on how you do it. I don't have an example. I just leave it to you to come up with some type, as long as it covers the 3 major areas. One is introduction, which includes the purpose of the lab. That there. Again, I already told you the purpose of the lab is to become familiar with the robot by doing these experiments right there. And you list the two parts that there. The second part of the lab is your procedure. That's usually the longest one because that's the steps you went through. And you can do it as a list. First we did this, then we did this, then we executed our code, and then we had to modify it 6,000 times in order to actually pick the thing up. That there, and then we cheated by moving the thing over to it as the arm started moving. That there, again, that there. And then your conclusion is basically a short little paragraph. And I've had conclusions, and I don't take call for them. As long as you're honest, that simply says that this lab was a complete waste of my time, and I don't know why I did it. And I've actually had some lab reports that had that in there. Or, this was helpful. I have a better insight of what a pain in the neck it is to program a robot. And programming robots this way is a pain in the neck. That's it. So, that's it. So, but you would submit this through the e-learning site right there. And then the second thing I had you do was shoot a short video where you would submit that through right here. And it looks like three people submitted their videos that there. And of course, I can look at the video and say, right there. And now we see who submitted it up there. And I can go through and click on that. And I don't know where's the video at that there. Supposedly I can download the video and look at it right there as I'm grading it that there. So this is the way that I'm having you submit the reports. And the reason I'm having you submit the reports this way is simply because I don't want a desk full of paperwork right there. So, and I tend to lose them, so that's it. Actually, I've never lost anybody's homework, but I don't have a whole lot of space in mine. Okay, well, on to our discussion for the day, right there. And I've got, yeah. No, I don't need a hard copy. I do not need a hard copy. So if you get your lab report done during the break, submit it during the break. I won't look at it until I get back. That there, unless the weekend, when I get back, not this week, next weekend, I might look at it. What's that? The sketches, you could just show one sketch for the whole thing showing that there. But yeah, your drawings that they don't have to be, there would be 6 drawings for all 6 motors. So you have 6 drawings up there, and that would be part of your step that there. So the first thing we did, we found the range of each motor. That there, and they don't have to be professional drawings. I suspect that there, a drawing that looks like this for the first one. Here's your box, like this. Here's your robot. You can see this is 0 degrees and this is 180, like that. The next one is here's your arm, right, going up, and you can say this is 180 and this is 0 or whatever it is. Right there. They can be very simple drawings like that there. You don't have to go through and draw the whole robot very precise and neatly that there. But just basically a simple one. The next one is showing, the next one is right here, and you can show what its range is right there. Of the motors, yeah. Again, it could be 0 degrees, 180. Then again, 180 should be like this right here, but that there. But just simply a drawing showing this is 180. That there. Then the next one, again, when you look at the pincher, you can say closed is equal to 0 degrees, and open is 180 right there. You don't have to draw the last one. You just simply say open or closed. That there. And then the wrist, the wrist movement like this right here, you can show that this is 90, this is 10, this is, whatever your wrist motion was for the hand. So you should have, there should be 6 drawings, well, it should be 5 drawings, and then the last one would be for the gripper. You can just tell me what's open and closed. Because the gripper is only open and closed, right? That there. So, that there. So you should have 6 or 5 drawings and just tell me the range on the gripper right there. So that there. So you have, like I said, that there, and then the last one is actually kind of harder because that was all just trial and error. You just simply say that we guessed at it here. This is our final code that we came up with. And then your conclusion is what did you learn? What didn't you learn? What was valuable from the lab? Just your conclusion. What did you learn from doing the lab? Right there. And what would you do differently? What didn't work? What problems you had? That there. So, there. Then of course the video is just the short little one where you show the demonstration of it picking something up. That there. And again, I'm expecting each person to write their own report, but then you're going to be sharing the same data. So I suspect that the groups are going to probably be somewhat similar, especially on the procedures. Because your procedures are going to be the same with all 3 of you in the group. Your introductions and your conclusions should be a little different right there. Because your conclusion in particular is what you personally got out of the lab. The introduction and the goal of the lab should be very similar with everybody in the room. Because the goal of the lab is the same. Although I don't expect one person to write it and everybody copy it. You're supposed to write it individually. That there. A number of schools, by the way, if you did that, they would probably just give you an F. It's called plagiarism when you copy somebody else's work and submit it as your own. Right there. So, I don't really look for plagiarism that much because I know it's a little bit more common here than it is in the U.S. The U.S. is very strict on reports. And if I got 2 reports that looked almost the same between 2 people, and I had 90% overlap between them as far as content, they both get big zeros. That there, because one person wrote the report or they wrote it as a group. That there, and the other thing is that, I have access to a software package called Turn It In, where I can submit your lab report to it, and it'll come back and tell me if you copied anything off the internet. Or that there. So it's actually a search engine that goes through the body of the report and tells me that 75% of it came from this website, or 60% of this section came from this website, or this publication, or this book. So there's all kinds of software tools to catch people who cut base from the internet. I don't apply them here, but I have access to them if I really wanted to be a hard nose about that. Just keep that in mind if any of you ever go to graduate school. Here at UDKL, we don't enforce it that much. I think the English department does, Gen Ed, I think General Studies does that there, but here on lab reports, we don't really enforce it that much. Okay, now that's the lab report. I'll take them all the way through the Monday after the break. That's there. So don't panic and try to get them in between now and Friday. That's there. But also don't let it go to where you ruin half your vacation working on a lab report. That's there. So, and again, it doesn't have to be real long. Don't submit a 10-page report right there. Okay, where was I on my PowerPoint slides? Okay, I stole these slides. I had some slides I used last semester, and I lost them somewhere. I don't know where they're at. So I had to panic today. I spent a lot of time today discovering that my Arduino board is fried, so I pulled out another development board I've never used before with a processor I haven't used very much before, and had to learn a whole new processor this afternoon, a whole new development system, so out there. But we've got basically 3 types of motors that we can use for robotics. And I just want to kind of go through the 3 types right there. In this particular set of slides goes into more detail that I'm concerned with, but I'll post some slides later that they're, and again, as you can see, it's labeled lecture 4, which means I swiped it from somebody else at there. And actually, the person I swiped it to didn't even put his name on it, so I can't even give him credit to who I stole it from. The website probably had who it's from but I just grabbed the slides. But the stepper motor we'll talk about a little bit later. I don't have a stepper motor but matter of fact, I probably won't go into great detail. DC motors are simple DC motors, and we usually drive them with PWM. I'll go through a demonstration later on those. Today I'm going to talk predominantly about the servo motor, but I'm going to go through these set of slides. And later on, I have a short little demonstration. Unfortunately, the demonstration on this one, there's no way you can see it, other than I'll make this guy attest that it's going clockwise or counterclockwise, right there. And the demonstration I've got is not as good as I normally would do with the Arduino, simply because I've discovered that the compiler I'm using, I downloaded a new compiler and I haven't figured out how to use it yet. I downloaded it at 4 o'clock. There, so, but we got 3 types of motors right there. A stepper motor is one where we've got some electromagnets right there. There's 4 electromagnets or 8 electromagnets, and we simply will energize 2 of those and maybe 4 of them in order to get our motor to go to a certain position right there. So if we energize these 2 steps up right there. Right there. If we energize these 2 motors, our actuator is going to go here. We reverse the direction of these 2, our arm is going to go the other direction. So if we make this the north and this is the south, it's going to go the other way. If we make this one here the north and this is south, it's going to go this way. And what we do is if we want to turn this thing, we go north-south, then we go north-south, then we go north-south, and we just simply rotate this thing around by energizing various and we can control the speed by how we send our pulses to that there. Now this is not a very good set of slides on stepper motors, But the idea is that we've got 4 outputs at there. In our 4 outputs from our processors, it's going to make one a north and a south right there. And we always energize them opposite of each other, so we only need, for any pair, 1 output. So if we have 4 outputs, we could have a north-south, a north-south, a north-south, a north-south right there. We can have 8 positions. We actually can get more than 8 positions by putting 2 of them high and 2 of them low. That puts us in the middle of that there. So we can control that with a microcontroller. Very simple. And I'll have a better set of slides when I have the lecture where I'm going to talk only on stepper motors right there. So, but again, this is here where they're showing here is that again we start out north-south right here, and we rotate this around that. And again, what you can see is that we can rotate this thing around. They show it in the various positions. This is not a good set of slides. I've got a better set of slides that there. A reference on stepper motors right there. And again, you can see that they're moving from north-south, and then I change this to north-south here. It goes on to the next set of teeth right there. Stepper motors are very commonly used in a number of situations. I used to have a big satellite dish and use the stepper motor to drive that. Stepper motors are used when we want to control position fairly accurately, right there. But they have the disadvantage that they require multiple outputs for the microcontroller. And they also don't have a lot of torque. Normally you have to use a gear train to torque in order to torque them up. So direct may oscillate. They're low resolution. In other words, you can't get super accurate with them. I mean, you've got 8 positions or 16 positions, depending on how many teeth you put in it. So you get an approximate location with them. So, but again, the main thing is we can set a particular position without using any feedback. Right there. And I'll talk a bit about feedback versus non-feedback right there. But there, as I said, my satellite position, I used to send in a particular code to the stepper motor, and it would move my satellite at 80, 90 degrees, a particular location. So stepper motors are used that there. Again, you can, here they're saying half stepping. That's what I was talking about, where we energize both these two. So it puts us in between the 2 teeth. It gets us a little bit more resolution. So in this particular case, we only have 2 outputs, and we end up with, instead of 4, but 8 positions. If we go with, 2 outputs, 3 outputs, that gets us, and I've never seen 3 outputs. I've seen 4 outputs. Usually they skip 3. We would have 4 sets, and when we have 4 sets, we'll end up with 8 positions. Here we've got, so I have such before 8. You did have 16 positions with 4 right there. So again, we look at our torque versus our angle right there. It starts off at relatively high torque, and as we get close to our position, the torque rolls off right there. More teeth. That there is how you increase. Again, they're showing right there. Again, the stepper motor gets you fairly accurate that there. Under damping allows oscillation. It's got some issues right there. Now, as we look at DC motors, a standard DC motor, you can't control the position of it. You can control the speed right there. But a standard DC motor, you put a plus bolt here, it's going to rotate a certain way. If I reverse the polarity, it will go in the other direction right there. In the microcontroller class, I think we talked a little bit about H-bridges. We'll talk more about that later on right there. But again, we continuously, this brush, what these brushes do is they reverse the polarity of the teeth right there, or of the motors right here. So as soon as we cross this right here, then we reverse the direction right there. So our stepper motor has two sets of, this one has two sets of north-south. This only has one north-south right there. So, and all we do is we just keep flipping the direction. As this thing rotates, once we cross it there, we reverse the polarity in order to get it to go the other direction. Right there. So it starts off north-south. Our magnet goes like this. And then as soon as it gets to the top, we reverse it to south-north. So it keeps on rotating. Right there. And that's a standard DC motor right there. So which one pulls more weight? That there, higher torque. These are much cheaper. Right there, the standard DC motor is much cheaper. Right there. This one's very durable. There's no brushes. If it's once it's locked into position, it's got a very high holding torque. Right there. And it's used for position control. You normally wouldn't use a stepper motor for a rotating, like a drive for a car or something like that. Although I've done projects where people have used stepper motors for that. Normally, if you're using a stepper motor, you're trying to position something right there. So, but stepper motors are used a lot in robotics, so are DC motors right there. So, a little bit of a concept here. I know that you are probably taking or have taken a course in feedback control systems right there. Does anybody know what I mean by feedback control? I think you shake your head. So, open loop strategy, we have a desired speed, we have some type of controller, we have a voltage, and then we have a motor, and we have our output speed right there. Now, when we're at open loop, we have no feedback. In other words, we don't know whether our actual speed or position is what we expect it to be. With a stepper motor, it's pretty accurate without feedback. Right there, because you've got your 14th or 18th or your sense of when I call teeth, I'm talking about the pairs of magnets that we energize or don't energize right there, and we can do the half stepping right there. But we know from the design of the stepper motor, if we set it a particular code, that we're going to energize a certain set of motors right there. So if we set it 1100, we're energizing the top and then the next set of motors, and we're going to put it in between. If we set it 1000, we're setting it right top center. If we set it 0001, we're rotating 180 degrees right there. So we have multiple, that they're actually depending on how we name our motors right there. I'm just putting an example. Well, if we set it a particular code on a 4 output, it's going to go in a certain position right there. So, I'll talk about stepper motors in a lot more detail in a later lecture after the break. So again, we have that there. Again, we also have open control for position right there. Now, most control systems that we're used to have some type of feedback right there. Now, an example of an open loop system is right now, I've got 2 switches over there for turning on the air conditioner in this room. There's no thermometer in this room to measure the temperature. So I turn on the air conditioner, it pumps out cold air, and when it gets too cold, somebody walks over and turns off one of the air conditioners. Well, that's our feedback, is that somebody, usually it's one of the young ladies there, women seem to get cold faster than men. I don't know why that is, but that's there. But every woman I've got to know is always freezing while I'm sitting there sweating. My wife used to, in the U.S., when it used to get cold, would sleep with 4 layers on and 2 blankets. And I'd be sleeping with a t-shirt and a pair of thin cotton pants and no blankets. That's there. Or maybe a thin sheet over top. And then I'd wake up in the room and say that, oh, it's so hot in here. And complain about how warm it is, that she's shivering to death. Now, some of that's being Malaysian and growing up in hot temperatures. I haven't talked much about where I'm from, but I grew up in Minnesota where it's minus 40 several times a year usually. And those of you who have never seen minus 40, I don't think That's it. In Malaysia, if you ever got to minus 40, most people would probably just die. That's there. They would just freeze to death because nobody's prepared for that. I see guys when I ride my bike to school at 7:30, 8 o'clock, are wearing winter coats. I'll put on a jacket because it is chilly riding a bike at 7:30. But I don't have a thick winter parka that I'm wearing. I've just got a little thin rain jacket. So, but again, when we're looking at their desired speed, if you like some people who, like some of the young men that ride motorcycles, their desired speed is you turn the throttle all the way to the maximum setting, and that's what your desired speed is. You don't look at the speedometer or see what your actual speed is. You just set the speed to full blast and you go, right? That's there. So that's again without feedback. It's like driving a car without a speedometer. That's there. You just put your foot down and whatever speed you have to be at, you're comfortable with. So most of us will, when it comes to cases of cars and velocity, the feedback actually is the driver. They're the feedback. You're going down the highway and the speed limit's 110. You figure 130 is close enough. So you get up to 140, you kind of take your foot off the gas. If you get down to 110, you tend to put it down a little further in the gas. But where you put your pedal is really the feedback. So that's called a man in the loop. Same thing with steering. You're steering your car with a steering wheel or driving your bike with a steering wheel. The person that's going to keep it on, or what keeps it on course, is the person driving the vehicle. That's the man in the loop. Now, Google and Tesla and all that want to take the man out of the loop and do automatic control of the steering right there. I know Ford has had for several years cars that they can park themselves right there. So you've got cars that will park themselves right there. So you don't touch the steering wheel. The vehicle actually provides the feedback and does the steering. Self-driving cars, of course, are supposed to remove the man completely from the loop. And when you look at the case of driving vehicles, 90% of accidents are caused by operator error. So removing the driver is probably the safest thing for cars. That's why they're doing it. It's not because they want to put all these taxi drivers out of work, although that's Uber's goal for self-driving cars is we want to get rid of the taxi drivers. Because taxi drivers, especially in the U.S. and Europe, are expensive. So, but again, we're looking at bang control is that you basically have no feedback and you control the speed various ways. And again, we have our controller for that there. This is talking about motors, and what we're coming up with here is that this is some kind of ratio right here. This is some constant times the desired speed, how much voltage we want to put times the speed. So if we increase the voltage, we're going to increase the speed right there. And our unknown is our torque. How heavy is our load? Anybody who's ever driven much, even a motorcycle, you probably realize that Malaysia's got some nasty mountains and hills sometimes. You drive from KL to Kuantan, or you drive you've got some hills to go over, right? And you got some hills to go down, right? Well, that torque is a function of whether you're going up or down the hill. How much resistance do you have? Now, if your vehicle's heavy, then that torque changes a great deal. If your vehicle's light, it doesn't change as much right there. So again, what we've got here is we're looking at a vehicle. This is some constant, and that's how much power we're putting to the engine, essentially, right there. But then we've got this loss right here. We've got a loss here, and that's the resistance of the vehicle divided by a constant multiplied by the torque, which is the reverse. That how much, our load. We don't know what the load is on our motor. That there. But again, as you go up and down hills, you probably notice you have to take your foot off and down off the gas right there. And that's where you need the feedback right there. If we knew exactly what our torque was, we could actually calculate exactly how much voltage we're going to need applied to a motor in order to get it to go a certain speed. Now there's speed versus voltage on pulse width modulation for almost every motor, and we can pretty much guesstimate how much current or voltage we need to apply, or pulse width we need to apply to a particular motor to get a certain speed. But the torque varies. You pull anybody travel, these luggage carts that you pull behind yourself, right there. You pull it on tile or a fully tile or cement surface, that thing rolls extremely well. You start pulling it across a rubberized surface, you got a little bit of a drag. That thing. And you pull it across plush carpet, and that thing feels like a boat anchor as you pull that thing. So again, the surface is going to make a difference. I used to be a runner. You can't believe I'm looking at my size right now, but I could go much faster on asphalt than I could grass. And the reason is whenever I took a step on grass, the ground absorbed some of the shock, where when I was running on asphalt, some of that, that shock was returned back by my shoes as part of the bounce right there. So I would end up with much faster speeds. And I know people that used to run on sand, and they couldn't go very fast at all because the sand would absorb a lot of the energy that they would apply. So again, this torque also varies with surface. Right there. You don't have, or at least I haven't seen in Malaysia, a gravel road. In the U.S., you can go to various places out in the country, and there's no asphalt on the road. It's just gravel out there. And the county would come and every so often put new gravel down out there. And that was what the road was. I said, I've never seen a gravel road. I've seen some dirt roads here, but I've never seen gravel roads. But gravel roads are very soft ones. You drive your car like in sand. It really weighs your car down out there. And you can't go very fast on gravel, which is good because you don't have much control on gravel anyway. And again, I used to know some crazy people that go 80, 90 kilometers an hour on gravel, and some of them completely wreck their cars after a while. But again, this is now we're talking about feedback. Right. Now, feedback basically means that we measure our actual speed, and then we have an error signal, is the derivation between your actual speed, and then we have our control system that would then turn right around and vary the voltage going to our motor. We're only talking motors out there, in order to keep the correct speed. Now, this could also be the correct position. The author of these slides put a nice little picture of Lombard Street, which I've driven down several times. It's in San Francisco. And it's known as the curviest street in the world. There might be curvier ones. The speed limit down the street is about 5 miles an hour. So that's about 8 kilometers an hour. But I guarantee you're not going to go much more than about 8 to 10 kilometers an hour down the street. And as I said, last time I drove it was in January of this year. My wife and I were in San Francisco, and I took her to Lombard Street just so she could see it. Of course, everybody takes pictures of it looking up at Lombard Street. Somewhere in my pile of pictures, I got pictures of Lombard Street with my wife standing in front of it up there. So I've been down that street. But this is a nice little picture that shows control system. Is if you didn't have feedback in terms of the driver, you would easily be going over those flat grasses there. And of course, I don't know how these people that live in these condos along Lombard Street stand the traffic, because it's non-stop tourists morning to night. Right? And at the bottom of Lombard Street, it's kind of an interesting thing, is if you look in this direction here, you can see Alcatraz, the prison on the island. It's a very famous prison in the U.S. called Alcatraz, right there. And Alcatraz is a prison built on an island in the San Francisco Bay, which supposedly no one's ever escaped alive from. But there are two people that escaped from Alcatraz, and they're not sure if they made it alive or not because they never found the bodies, but the guess is they probably didn't make it because they went swimming from the island. And it's a little over a mile to shore, and the temperature of the water is just above zero. It's very cold. And those of you that aren't familiar with geography, it's San Francisco's in California, which everybody thinks is this warm, sunny place. San Francisco's in Northern California, and California is probably about twice the size of Malaysia. And the weather from San Diego, where my son lives, there is very hot in the summertime, and very sunny in the wintertime. It gets cool, but never gets cold. San Francisco never gets warm. Never gets warm. I have not been in San Francisco where the temperature was above 15 to 20. That's in the hottest, July or August, the hottest. But we were there in January, and it was probably down around 4 or 5. So California is not this warm, sunny place that everyone talks about. Parts of California are, but parts of California are wet, damp, and dreary, just like London, right there. So, right there. Okay, this is getting more into the sensing. We'll come back to talking about the various sensors we'll use. Servo motors is where I'm going to talk about today. And servo motors actually are two types. One, and I've got one of both types here, right there. One is called a continuous, and then one's called a standard. The original one is the standard, and we send it pulses. Now these are relative numbers. 1.5 is supposed to be neutral. 1.25 is supposed to be 0 degrees. 1.75, and what we're sending it is what's called pulse width modulation, right there. Right there. And what we're sending it is, we've got a pulse that starts here, and it's got a width right here, and it's got a period of roughly 20 milliseconds right there. Right there. And we send it a pulse, right there, that's got a width. TW, the width of the pulse right there. And the width of the pulse tells the servo what position we want to be in right there. And on the servo motor, right there, you'll see a bunch of a board right there, right here. And this particular motor here is basically the electronics, and the controller is to tell it how to set the stepper motor in there. There's actually a small stepper inside the servo motor, right there. But we're sending a pulse right there. And servo motors are very popular because it only requires one output for the microcontroller, where the stepper motor requires 4, 2, 4, however many we want. So servo motors are very commonly used. Our robot that we used last week has 6 different servos. Now, as it turns out, we just set it in position. And here, what I'm going to do in my demonstration here is that I'm going to send it various pulse widths just to set the position to where I want it to be, right there. So this actually goes back more to the understanding of how a servo works, where the folks that wrote the software that went in the Arduino, actually, we set an angle between 0 and 180, and then they turn right around, and then they calculate what the pulse width is from our angle, and then they send that to the servo. Right there. Now, normally I will do this demonstration with an Arduino. I had mistakenly plugged in a 9-volt power supply to my 5-volt Arduino and sent it off to SmokeLand. In other words, it's no longer talking to my computer. So I will probably have another Arduino tomorrow or the day after, so I may repeat this demo when we get back. They're actually ordered another one to replace that there. So, but again, we're looking at here, our 150, it should be our 90 degrees, our 180 should be 1.25 milliseconds, and 1.75 is supposed to be that there. Now, my pulse, I'm setting something different for some reason, you know, I just experimentally tried it, and I may try a few more here. That's it. So again, what we've got there, the rest of these slides actually get into the coders. I'm not going to talk about those now. We'll come back to that there. So let me skip on that there, and let me go back to my right here. This is that slide just on Arduino, or on right there. Again, this is simply saying that these slides were stolen. I stole them from somebody who stole from someone else. So he's acknowledging who I stole. Again, he didn't put down who he was who stole them. He just simply says, here's some slides I stole from somebody else. But servo motors are used for angular positioning and radio controlled airplanes as an example. Our robots another example. Drones are another example. That they're typically they got 180 degrees. Some go up to 210. The shaft right here. This is what a servo. This is what the servo looks like right here. This is one type of servo right there. This shaft will only rotate from here. That's one direction, and there's the other direction. There's a stop. It won't rotate the whole way. Right there, and it's not very powerful. They're simply saying it's rated at 40 ounces. Divided by 0.21 means that 1 inch from the hub can serve about 40 ounces of force right there. It can move 60 degrees in 0.21 seconds. Right? So again, that's not a lot of force right there. Now, it's enough to control much larger motors right there, and we'll talk about that there. Servos are constructed out basic DC, some gear reductions, a position sensor for the shaft. So they're talking about these are using DC motors on stepper motors, electronic circuit that controls it there, and basically it has a gear ratio up there. So typically a potentiometer measures the position that they're. So the feedback is in the servo motor. So it's got feedback within the motor to tell what its position is. Right there. So we don't have to apply any feedback to it. Right there. So they are you can get them very accurate. Unfortunately, our robots use cheap ones like this here, and they're not real accurate. These aren't super accurate. Right there. These are hobbyists type. Right there. They're like 2-3 ringgits a piece. You don't spend a lot of money for these. Right there. So these are closed loop right there. So we send a signal, it goes to the motor, it goes in one direction. Closed loop means that we check to make sure it's at the right position. Right? So these are closed loop. Now again, they're talking about here, they're using 1 to 2 milliseconds. That previous one said 1.5 to 1.25. It varies with the motor actually. And I don't have a data sheet, so I just guessed at different values that I put in there. That's it. So, control wire, commutes the desired position, and then we have VCC and ground. So we only have one wire there, and the servo expects to see a pulse at 20 milliseconds. That's there, and if we give it a pulse of 1.5 milliseconds, it's supposed to go to 90 degrees. If it's shorter than 1.5, it should go closer to 0 degrees. If it's more than 1.5, it should go towards 180 right there. So we have the pulse width determines the position, and it's fairly accurate. Now, unfortunately, I'm using some software for a brand new controller that I've never used before out there. So I had the fun of learning a new processor this afternoon. Out there. And for those of you who took the 8051, you know that I tend to like to use that one. Out there. I normally use for this particular demo the Arduino, which I've used many times before. And unfortunately, my Arduino was dead, so I had to grab a brand new one that was in the package I ordered to learn, but I didn't expect to learn it in a very short time. Out there. But fortunately, I got to work halfway. Out there. So that's it. Now, again, this is what they're showing is going from 1.5 to 1.25 to all the way to 1.75. I think the software I'm doing only allows me to put integers in, so I can only put 1 and 2. I downloaded a better compiler and I have not used it. So I'm using an online compiler. And you're talking about a really weird way of programming a processor. You'll probably appreciate the 8051 software a lot when you see what I'm having to go through with this one. But that's it. Before I get there, again, I'm not going to worry about that there. Modified basically means, and this is a modified, also referred to as a continuous servo, so it can go clockwise or counterclockwise. Unfortunately, I didn't bring a screwdriver. I could move the shaft over here to show what that's there. Actually, I leave this one without the shaft because I want to know which one it is. If I put this thing here on that there, then I don't know which one that there. So you're going to be my witness to tell me what direction it's moving. Right there. So, right there. So if I set a pulse of 1 millisecond, it'll move clockwise. If I set it 2 milliseconds, it'll move counterclockwise. And I can vary the speed by varying the pulse width. Right there. Unfortunately, since I can only set it at 1 or 2, then I can only run at full speed in both directions. Right. So again, the modified, they simply, again, they're called modified because initially people were taking these apart and modifying them to be continuous. Right there. And now they make them as continuous. Right there. So again, parallax are there. Just again, we don't have that there. But this is kind of the way it looks right there. This is, and both of them work the same way right there. They look the same way. I've got a little connector right here, which I'm going to connect to my processor board here in a few minutes, right there. And this is how you would connect it to, now again, this is the software for, right there. The last thing I'm going to do is bring up my web browser of all things. And in my web browser, this is the slickest little thing I've seen and the most painful thing I've ever had to work with. That's there. The actual compiler is on a website. That's there. So you write your code on the website, right there. And then you compile it on the website, and then you download the code and copy it to the processor board. So it's kind of an interesting way of loading it that there. But the way it works right here, and this one here, I'm not sure where I'm at, but let's just set this to 1 right now. And what this code here is, it's a little hard to see, is I'm setting our period in 20 milliseconds, and I'm going to set it at 1 millisecond pulse right there. And I just got a little thing. I tried doing it where we go back and forth. It doesn't work for some reason with this processor. So I can change it in the code and move things around, but I can only do one move at a time, and then I have to edit the program and do it again. And there, why it's not working is probably something very simple that I did wrong. Again, as I said, I did not look at this website till about 2 o'clock this afternoon when I gave up on my Arduino and I started looking for another way of doing it. It might have been closer to 3 o'clock, so I had about 2 hours to figure out not only how to learn this, how to program this processor, but to get to a compiler and figure out what pins I'm going to. So that's there. So it was actually, even for me, it was pretty amazing that I got to work. That there. So again, what I'm going to do here is I'm going to plug this in, and this one here I'm going to hook up to the wrong one. Make sure I put the wires in right. This is actually a much more expensive board than the ones that we use for the microcontroller course. It's a really nice processor. I just haven't had time to play with it until today. And that's the way I typically learn things, is at the last minute. So I'm just going to plug this in. Right there. Now, when I plug this thing in right here, I compile my code right there. And as I said, you know, it's a preview compiler and it's fairly quick. Now the way that it works, I bring up my folder and I just right click that and I just simply say send to the board. Once I send it to the board, you notice that it turned right there. That's all it does. Right there. If I send it to it again, it's not going to turn because it's already in that position right there. And it just kind of, all right, I'm already here. I go back to my code and I change this to, and I'm going to say just 2 right here. And we can try various ones. I compile it again right here. And I have to show it in the folder, right click it, send to my board, and just notice that it moved. And I went back to the other position. Now what I tried to do, and you would think that it would work very fine, is I tried to write a loop where I would send it a 2, then I would send it a 1, right there. Right there. And who knows, it might work now that I'm in a group of people, here. Right there. And let me just grab this. Control C. Control V. And I'm going to send it 2, then I'm going to send it 1. And I'm going to wait 5 seconds, 4 seconds in between right there. And so supposedly it's supposed to go back and forth. For whatever reason, it doesn't want to work, but I'm going to just show you that I tried. That's the way you would get to go back and forth. So we compile it. And you notice I get a whole bunch of these from various trials. Actually, I had like 25 that I deleted them from doing trying different things here. But I send this to it, and see, it just does nothing. It just sits there. It just moves right there. It doesn't like that for some reason. If I run the program and just tells it to go one position, it works perfectly. Right there. So it tells me there's a problem with the compiler and sending that there. And again, I'm resending it. I shouldn't have to set the pulse width each time. Right there. That there, you know, you should just be able to change the you see that doesn't fix it right there. Now it just kind of stares at me. Right there. But if I go back here and I delete this. And delete this right here, right there, and I compile it again. This I'm setting it to 2, it may not move much. Show in folder. See, it's not jerking anymore, but let's go back and let's send it. I'm going to try sending it 1.5 and see what happens. I'm thinking this particular right there, compile. I don't know why I put down the bottom there. Yes, it moved 90 degrees up there again. So So I sent it one code, it worked perfectly fine out there. And this is a case, you know, and I told you in the microcontroller class that every now and then things don't always work as they're supposed to. This is a case that don't ask me why I cannot get it to go back and forth. With the Arduino, I can. And I think there's something wrong with this compiler, the way that it handles that PWM width, you know, when it sees it the second time. I think it's got a glitch that there. So now if I go back to the same thing, again, I'm just going to take and put the continuous here in. After 1.5 it's supposed to stop. I'm going to set it at 1. So that's moving fairly slowly there. That's a bearing that's going off, makes that noise. Fortunately, I've got another one of these. Oh, wrong one. Alright, this is now going counterclockwise. Put your finger on it, you see it goes counterclockwise, right? So it's now going counterclockwise. I go back to my code here, and I change that to a 2. That's there. Now you can see, it goes the other direction now. So I can control the direction right there. Now theoretically, I should be able to control the speed right there. This should go relatively slow, but I think again, my compiler is not see, I'm getting the same speed. This compiler is not giving me the right pulse width. And so the compiler is worth what I paid for it. It's, you know, it's a freebie that, you know, now it speeds up a little bit. But so the compiler is not giving me good code right there. So I downloaded another compiler. Unfortunately, what I downloaded was the full version of the full Kyle for the ARM processor. And it's got a learning curve of probably about 10 hours. And I didn't have 10 hours today to figure it out. So when I said I didn't have 10 hours to figure it out, my solution for the future was to get a replacement Arduino and use it for my up there. And to kind of show you, the Arduino code is very much like what we ran on the, you know, when we write our stuff for MATLAB. So all we're going to do, this is for a particular code. This is what I was trying to duplicate today, is that I could go, this is going through and going from one, you know, going between 0 and 180, and it's going very slowly right there. So I'm passing the angle, and then I'm, you know, here I was doing this with 2 servos. One would go in one direction, one would go in the other. Right there, and this was again going the other direction where I'm going faster right there. So there, file, open, continuous right there. Again, I would tell it right here that I'm going to write, but the Arduino has a library called servo.h built into their compiler right here. And this actually is a sketch. This code's a little simpler to see too. That I just simply tell it that I'm going to attach an Arduino to pin 9 on my microcontroller on the board right there. I attach a scope on pin 8 so I can look at the signal right there. And I can send it a pulse width of 1.8 milliseconds. It's going to go clockwise. I delay 2 seconds, and then I'm at there, and then I'm going to go counterclockwise at there. You know, one's going clockwise at there. You know, I copied the code and I didn't update that there. I just changed these directions right here, right there. And that's the way the Arduino code works. It's much simpler. But you don't actually, but again, you're giving it the pulse width right there, is what you're giving it up there. But this will automatically set the period 20 milliseconds and send it to that there. And it's very simple. One of the problems I had using this code is that if you look at this right here, PWM out is called my APM, and it's attached to pin PWM out. And unfortunately, my documentation didn't tell me what pin that was. And when I looked at this board, there is PWM/MOSL/011, PWM/CS010, PWM/02, PWM/05, PWM/03. I mean, there's all kinds of pins labeled, and it actually turned out to be on PWM/03 is that there. So their documentation is somewhat lacking right there. And the reason is that this software was written for any ARM processor, and I'm using a particular ARM processor with a particular pin out there. So they just say pin PWM, and I don't know which pin that would end up being on this processor right there. So I have a little trouble with the compiler. So I was going through pin by pin trying to get this motor to work, trying to figure out what pin is PWM_out. You know, I have no idea what pin that is, because there's 6 different PWM outputs on this processor. So which one is that one right there? Where when I look at the Arduino code, I immediately know right here that I'm attaching it to pin 9 of the processor. So there's 6 or 7, you know, I think there's like 4 or 5 PWM outputs from the Arduino, or at least 6, because we got a 6 servo motor being run with Arduino. So there's at least 6 PWM outputs, and you tell it which pin number you want it to be. The code that I was running today with this processor right here, I had no idea what pin number is what. That there, no idea. So I was going through just trying pin by pin till I got my PWM output. I could see it. After I had the scope out, looking for it on the scope. I wasn't running with the motor. I was looking for the scope output that would give me, would show me the signal. That there. So I had a very challenging afternoon. You know, Ibrahim kept looking over my desk, waiting to know if I wanted to take a break. And it was like, no. So maybe that's what's added to my head today, is stressing to make sure I got a demo to work. To show how actually servos work fairly easy. My problem today was learning a whole new processor and a whole new operating system. If you can imagine learning your 8051 operating system, you know, compiler and everything, the first time without an instructor, that's what I went through this afternoon. Is that I was using a whole new compiler, whole new version of C, whole new processor, and I had an afternoon to figure it out. And actually not a full afternoon, I only had the time after I discovered that my Arduino was dead. But that's what engineers do, right? I had a problem, I pulled up, opened up my desk, oh, here's a processor board, I bet you I can make this work. And I made it work in a few hours. Not perfectly, but I got it to work. Now the challenge is to figure out the compiler and get to work with that. I am going to quit at that. I actually did go about an hour and 15 minutes. That's about as long as I normally go. Right there. I think actually, we were actually late starting because we had to find a room. And actually this room was just barely big enough for who showed up. Right there. So, right there. Everyone